Alright, so let's complete this section. But before we see what else is there in this section, let us go back briefly and see what we have done so far. We started our journey with this class of functions where the elements are PC functions, piecewise constant functions. And of course, when we say functions, we are talking about real valued functions whose domains are bounded intervals. Okay, that's understood, that's there in the background. We first developed a theory of how to integrate the elements of this class, and then we extended our definition of integrability to include all bounded functions. PC functions are automatically bounded, so that means this is an extension of the existing theory of integrability. PC functions all are integrable. Okay, so there is really no question of integrability when you talk about PC functions. However, when we go to the larger class of any bounded functions, then integrability becomes an issue. But we did so we developed the theory, and then recently we have proved that some special types of bounded functions are Riemann integrable besides PC functions. They form another class of functions of bounded continuous functions. We do not mention boundedness for PC functions because they are automatically bounded. But continuous functions are not necessarily bounded even when considered on a bounded interval. But besides these functions are also Riemann integrable. Now the question is, can we enlarge these classes of functions even further to include more general functions which are also Riemann integrable? And the answer is yes. So in the rest of this section, that's what we are going to see. And this definition, it defines such functions. So let's see what this definition is. Let I be a bounded interval and let f from I to R be a function. We say that f is piecewise continuous if there exists a partition P of the domain interval I such that the restriction of f on the subinterval j is continuous for all j belonging to the partition P. That means a piecewise continuous function is a function defined on some bounded interval I, parts of which are continuous. So there exists a partition P of your domain I such that on each part of that partition, on each subinterval of that partition, if you consider the function, that is, if you restrict the function to that part only, that much is continuous. continuous, and this is true for all the parts. So you immediately notice one thing. PC functions are automatically piecewise continuous. How? I mean, without being too specific or too rigorous about it, you just think of the graph of a general PC function. Say it's defined on this bounded interval. And when I say without being specific, I am not mentioning whether this interval is open or closed. Let's not consider those things. So this is the bounded interval, and say this is a partition of the interval. The graph of a general PC function, I mean a piecewise constant function, is going to look like this. So on the individual parts of this interval, so these are the j's of that partition, the graph is constant. So if you restrict your PC function to each of these intervals, then it's a constant function, and constant functions are automatically continuous. We already know this fact, and that's why all the functions in this class of PC functions, are also in this large class of piecewise continuous functions. Piecewise constant functions are also piecewise continuous functions. But what about the functions in the second class? These are bounded continuous functions. Well, if you ignore the boundedness for now, I mean, of course they are bounded, but because they are continuous, so automatically these are also piecewise continuous. Why? That's because there exists a partition P of I, which is singleton, which has just the interval I itself. That is also a partition of P. Now, if you restrict your function coming from this class to this sole element of P, then you actually get just the entire F. And F is already continuous, so by definition, that such an F is also automatically piecewise continuous. See, there is a temptation to abbreviate this one also as PC, but then we will get confused between this one and this one. So whenever we want to write piecewise continuous, we will write it fully, and we reserve P dot C dot for piecewise constant. That means both these classes are subclasses of this large class of piecewise continuous functions. Okay, and now we are going to see this result, which will say that if a bounded function is piecewise continuous, then it is still Riemann integrable. So far we have seen that if a bounded function is continuous, then it's Riemann integrable, but this is even more general than that. Continuity throughout the interval is also not needed. If there are finitely many breaks, finitely many discontinuities, so that it is, I mean, the function is piecewise continuous, then also integrability is restored. Okay, it is there, it doesn't go. But before we get to that result, let's see one example. And that example is this. It's a very simple example, but nevertheless, let's just see what it is. Define the function f from the closed interval 1, 3 into R by this rule f of x equals x square if x lies between 1 and 2 in this manner. X is, of course, it has to be greater than or equal to 1 because it has to come from the domain, but it's less than 2, and when that happens, then the output is x square, and the function is equal to 7 if x is equal to 2. So when the input is 2, then the output is 7, and the output is x cubed if the input is greater than 2 and less than or equal to 3. This is not a piecewise constant function. Okay, it's not piecewise constant, but it is piecewise continuous. Then f is piecewise continuous since if so now we have to give the partition that will make it happen, but it's almost clear what the partition should be. If P is the partition closed 1 comma open 2 comma the singleton set 2 comma this. Okay, if this is a legitimate partition of we need to write of the domain 1 comma 3, then this is continuous for each j belonging to P. I mean, you can clearly see why that is so. For example, the restriction, this restriction when j is this, is the ordinary square function, which is continuous because it's a polynomial function. On this degenerate interval, which has only one point, also it is continuous, it's constant function 7, which also is a polynomial, and on this subinterval also it is a polynomial function, cubic polynomial, so again it's continuous. So that's why this is an example of a piecewise continuous function, but note that the entire function f is not continuous. In fact, let's just write that. Note that f is not continuous. For example, f has a discontinuity at the point 2. Okay, at the input 2 there is a discontinuity. Alright, so let's now finally state this result. So this result, which is a proposition, will subsume the previous results as special cases. I mean those two classes. And we have already seen that now the functions we are talking about form a larger class of functions which includes both of those classes as subclasses. And we are now saying that in this class also all the elements are Riemann integrable. So that way we have found a very large class of integrable functions. This is not going to be the largest class though. We will see that some other very large class, something like this, also has all its elements Riemann integrable in another section. Okay, so what was I going to do? Oh, I have to state the proposition. Let I be a bounded interval and let f from I to R be a bounded piecewise continuous function. Then f is Riemann integrable. That's the result, and its proof is the only exercise of this section. So we will see the proof in the community section next Sunday. For proof, see exercise 11.5.1, and this is where the section ends. I mean, its theory part ends, and once we prove this, the section will be completely over. And that's just it for this video. It is short because this is what we had in this section, and I don't want to start anything new now itself. Well, how can I start anything new unless we solve this? Okay, so that's just it for tonight, and tomorrow we have number theory, but we also have trigonometry from class 11. So we will do both of these things. Okay, so see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.